Today we want to talk about finding some of these trig ratios when we're on the coordinate plane and we're dealing with points on the coordinate plane, points that are on the terminal sides of these angles, and how we can find all 6 of the trig ratios now that we know there are 6 trig ratios. So let's take a look at that. So let theta be an angle in standard position and point xy be any point on the terminal side. Let r represent the distance from the point xy to the origin. So if we have some point here, and this is that point xy, and it's on the terminal side, we're designating that r is the length of that terminal side. And we use r historically because of radius. You know, if we're drawing a circle, going in a circular motion around the origin, that would be the radius of the circle. So historically, we use r for that. And if this is the point xy, then the side, this leg of the right triangle is x, and this leg of the right triangle is y, and that radius is the hypotenuse. And then we're able to say, okay, well then the sine of angle theta would be the opposite over the hypotenuse, which would be y over r. The cosine would be the adjacent over the hypotenuse, which would be x over r. And tangent would be opposite over adjacent, which would be y over x. What we learned about the reciprocal functions, the reciprocal trig functions, is that they're the same ratios, just the reciprocal. So sine has to go with cosecant, because there always has to be one with a co and one without a co. So sine goes with cosecant, so it's just going to be the reciprocal of sine. So it would be the radius over y. Secant is the reciprocal of cosine, which means that it's going to be equal to r over x. And cotangent goes with tangent, so that means it's just going to be x over y. And that would be true for any of the points that we could write on the coordinate plane. So let's see some specific examples of what that might look like. So we have a point 4, 5. So we know that this point is 4, 5. So that means that x is actually equal to 4, y is equal to 5, and I don't, from this point, have what the radius is equal to, but that's why we have the Pythagorean theorem. It's a right triangle. I can find that radius length. I just have to do 4 squared plus 5 squared is equal to r squared. And I hope you picked up on the fact that I didn't use the Pythagorean triple because that 5 was not the hypotenuse. For it to be the 3, 4, 5 right triangle, the 5 has to be the hypotenuse. And here the 5 wasn't the hypotenuse. So that's going to be 16 plus 25, which is going to be equal to 41. So this radius is going to be the square root of 41, because we'll have to take the square root of that side. So now I have my opposite, my adjacent, and my hypotenuse, and I can find all of my ratios. So sine is going to be equal to 5 over the square root of 41, which as a ratio, I would be done. It's problematic, though, because that radius is the square root of 41, and I have to rationalize that denominator. I can't leave it that way. So I'm going to have to multiply the top and the bottom by the square root of 41. And when I do that, I end up with 5 square roots of 41 over 41. So don't leave something with a not rationalized denominator. That's not going to be cool. Cosine's going to run into the same problem because adjacent over hypotenuse is going to be 4 over the square root of 41. but I have already rationalized one of them, so I kind of get the pattern here. If I multiply the top and the bottom by the square root of 41, I get 4 square roots of 41 over 41 for my cosine. Now tangent looks like it's going to be a little easier because it's going to be 5 over 4. And I don't have to rationalize anything for that one. Now cosecant, I want to flip, and I end up with the square root of 41 over 5. Well, that one doesn't need to be rationalized. Woohoo! If I flip cosine, I end up with the square root of 41 over 4. Also doesn't have to be rationalized. And cotangent would just be 4 over 5. So the good news is, if sine or cosine has to be rationalized, the reciprocal of it usually does not. And vice versa. So usually you're not having to rationalize all of them, which is nice. Now, we do want to pay attention because these points are not always going to end up in quadrant 1. And so the negatives and the positives have to be paid attention to. For the point -4, -5, that's going to end up down here. So the point -4, -5, so this length is going over to -4. This is going down to -5. That radius, when I do -5 squared and -4 squared, they both become positive. And so that ends up with a square root of 41. And it doesn't have a sign to worry about. It's just positive. Because it's the radius. It's not the actual coordinate on the coordinate plane. When we look at our opposite side, though, remember our reference angle is right here. So the opposite is -5. The adjacent is -5. So the sine is going to be -5 over square root of 41. That's going to be negative. And it does still have to be rationalized. So I make sure I rationalize it. And I get -5 square roots of 41 over 41. Cosine. Cosine is going to be adjacent. So that's -4 over square root of 41, which has to be rationalized as well. So I get -4 square roots of 41 over 41. And tangent is going to be opposite over adjacent, which is going to be -5 over -4, which is going to be positive 5/4. What we find is that tangent is positive in quadrant 1 and quadrant 3. Tangent is negative in quadrants 2 and quadrants 4, if you recall that from last year. So that's important to know which quadrant is tangent positive and negative in. Which quadrants are sine and cosine positive and negative in. That's important as well. Cosecant, though, is just the reciprocal. Flipping the fraction doesn't change its sign. So this is just going to be negative square root of 41 over 5. This will be negative square root of 41 over 4. And cotangent is going to be 4 over 5. So again, the signs don't change for the reciprocal functions. You're flipping them, but the sign is going to stay exactly the same. Now, the last question here, the last part of the question, let's take a look at that. If we have a point at 1, -9, that's going to end up in that fourth quadrant. And so this is 1, and this is -9, and that is actually going to be our reference angle. If I do my Pythagorean theorem, 1 squared plus 9 squared is going to be equal to r squared. So that's going to be 1 plus 81 is equal to r squared, and I get 82, and the square root of 82. 4 will not divide that, so I don't know that there is a perfect square that will divide that, so I don't think that reduces. I think it's just going to be the square root of 82. So when we find our sine, our cosine, our tangent, we want to remember sine is opposite over hypotenuse, so that's going to be -9 over the square root of 82, which is going to be -9 square roots of 82 over 82. It is negative. Cosine, though, is the adjacent. It's positive. So 1 over the square root of 82 is going to end up being square root of 82 over 82, but it's positive. And tangent is going to be opposite over adjacent, which is going to be -9 over 1, which is just going to be -9. When we do our reciprocals, we end up with negative square root of 82 over 9, positive square root of 82. You could put over 1, but we know over 1 isn't necessary. And then our cotangent is going to be -1 over 9. But now it is asking us to find the actual angle of rotation of theta. If you are asked to find the angle of rotation, we do remember that that's why we have our inverse trig functions. We can use the inverse trig function on our calculator to help us find what that angle is. But what you have to be aware of is that the trig when I go into my calculator and I type in inverse sine of -9 square roots of 82 over 82, what it gives me is -83.7. And so we always want to make sure that we're paying attention to directions. We're paying attention to units of measure. For example, this just said to find the angle of rotation. It didn't say specifically that the angle had to be positive. It didn't say specifically that the angle had to be between any two particular measures. And it didn't say whether it had to be radians or degrees. But what you're going to find as we move forward in this unit, as we start solving equations, the angle that it is in between is going to matter. And so -83.7 makes sense because that would be going this direction. It would still be shy of 90 degrees, so it's in the fourth quadrant. It's pretty far down here, which would make sense if this was 1 and -9. -83.7 seems like it would be in about the right position. But if it had asked me for some angle between 0 and 360, -83.7 wouldn't be it. It's a negative angle. And so I would then have to say, well, if I want to know what the positive angle is for that, I would have to do 360 minus that, which would be 276.3 degrees. And so this would be the positive angle of rotation for that terminal side. This would be the negative angle of rotation for that terminal side. So always pay attention to the directions when you're doing those inverse sine and cosine functions because they're really dealing with reference angles. They don't like to give large over 90 degree angles, and so they are set up to the trig ratios for the actual right triangle. So that's why they're always going to give some kind of of reference angle there. And you have to know which quadrant do you want it to end up in. All right, so let's take a look at another example. So if it's negative 12, 5, negative 12, 5 is going to be in quadrant 2, I believe. So this is negative 12, and that's positive 5. So if we're doing the Pythagorean theorem, I believe this is one of our triples. 5 squared plus 12 squared is going to be 25 plus 144, which is 169. Yes, that's what I thought. It was one of our Pythagorean triples, so that's going to be 13. So sine is going to be opposite over hypotenuse, which is going to be 5 over 13, and sine is positive. And cosine is going to be negative 12 over 13, which is negative. And tangent is going to be positive 5 over negative 12, which is going to end up being a negative 5/12. And we didn't have any denominators to rationalize, which makes finding these super easy because we're just going to flip them. So 13 over 5, it stays positive. 13 over 12, it stays negative. And 12 over 5, it also stays negative. So that gives us all of those. But again, when I go into my calculator and I type in inverse sine of 5/13, it gives me 22.3 degrees. That's not the right answer, because 22.3 degrees would be in quadrant 1. What you have to remember is that the calculator is going to give you the reference angle for that ratio. We have to know which quadrant it's in. I know that this one is in quadrant 2. That 22.3 is that angle. But the angle I'm looking for is this one. So I don't want to forget to take 180 and subtract 22.3. So that's going to get me 157.7 degrees, because that is the actual angle of rotation. 22.3 is the reference angle. Sometimes they don't give us all of the information that we need by giving us the point. You know, giving us the point tells us exactly which quadrant that it's supposed to fall into. But here they're actually giving me some of the ratios. For example, they say that the sine is equal to 2 over 7. The other piece of information that they've given me is that the tangent is negative. Remember, if the tangent is less than 0, it's a negative number. So that tells me that the tangent is negative. We just discussed how tangent is positive in the first and third quadrants, but tangent is negative in the second and fourth quadrants. So if my tangent is going to be negative, it's going to have to be in the second or the fourth quadrant. The sine turned out to be positive. Sine is always positive in the first and second quadrants, and sine is negative in the third and fourth quadrants. So this tells me that the sine is positive and the tangent is negative. So that means it has to be quadrant 2. So in order for the sine to be positive and the tangent to be negative, the point I'm discussing is over in quadrant 2. So I know that sine is the opposite over the hypotenuse. So this tells me that the opposite side must be 2 and the hypotenuse must be 7. So I can still use my Pythagorean theorem to figure out what that other side has to be. So 2 squared plus b squared is equal to 7 squared. So 4 plus b squared is equal to 49. B squared is equal to 45. And when I take the square root of both of those sides, I end up with 3 square roots of 5. Now this is where I do want to pay attention to the quadrant I'm in. I'm in the second quadrant, so this has to be -3 on the square root of 5 because that's the x coordinate, so it's over to the negative side. So now I know that my cosine has to be adjacent over hypotenuse, so that's going to be -3 on the square root of 5 over 7. And when I do opposite over adjacent, I'm going to get 2 over -3 square roots of 5. But I'm going to have to rationalize that denominator by multiplying the top and the bottom by the square root of 5. And that's going to give me -2 square roots of 5 over, and this is going to be 3 times 5, which is 15. So my tangent turned out negative, my sine turned out positive, and everything is as it should be. Now, again, we just have to do the reciprocals. So cosecant is going to be the reciprocal of sine, so that's just going to be 7 over 2. When I do the reciprocal of cosine, I get -7 over 3 square roots of 5, but I am going to have to rationalize that. And that's going to end up being -7 square roots of 5 over 3 times 5, which is 15. And then when I reciprocate, do the reciprocal of tangent, that's when I end up with -3 square roots of 5 over 2. And so that gets me all 3. And it didn't ask me for the angle, so I don't have to worry about that. But I was able to find all of my sines and my cosines and my secants and cosecants using the clue that they gave me to help me find my angle.